Okay, in this example, we're being asked to determine the nature of the stationary points. Back to determine the nature of stationary points. On the graph, f of x is x to the fourth minus 4x cubed. Now, x to the fourth we're not that familiar with. It's possibly has now 3 turning points. Remember, x squared had 1 stationary point or 1 turning point. X cubed had a maximum 2 turning points, 2 stationary points. X to the fourth has a maximum 3 stationary points or 3 turning points. So it could be something like this, this, and this. So 1, 2, 3, or 1, 2, 3, 1, 2, 3. Could go off like that. Yep. They could be very general examples for x to the fourth. You saw me draw in a previous example that x to the fourth was actually a very flat-based parabola. Well, that's true. When there is nothing more complicated than just straight out x to the fourth, that's what the graph looks like. This one's going to be more than that because of the presence of the x cubed. To me, it looks like it's going to be very positive, so I would rule out this one and possibly this one. But we'll see. It may not look anything like that. Always a bit of a good idea to have a general concept of what the graph might look like. Okay, so 1, we'll be determining the nature of the stationary points. 2, identify any points of inflection. And 3, sketch the graph. We've really got a lot to do here in this example. So back to determining the nature of the stationary points, use the wording of the question to begin your solution and say, to determine the nature of stationary points. How would we complete that? We would solve f dash x equaling 0. We want, for a stationary point, we want the first derivative to be equal to 0. The second point, second part to the question, identify any points of inflection. Well, that's the one we've just been looking at in this exercise. To identify points of inflection, solve f double dash x equal to 0 and show concavity changes. Please do not be satisfied to stop after that. And it's what most students do, and they lose marks for it. So be aware. I'd made this actually my first point when I introduced identifying points of inflection, because it is critical that you do it. It's hard to show that concavity changes until you've done this, and this is why I would write it now in this order. I'll pause the video. I will find the derivative, solve it equal to 0, and have a look at the values of the gradient either sides of the stationary points and come back and talk about it. Okay, there's quite a bit happening with this graph. So let me try and break down all of this that I've written here. So remember, the first thing was to determine the nature of the stationary points, and to do that you solve f dash x equal to 0. So f dash x, because remember f of x is x to the fourth minus 4x cubed, so f dash x would be 4x cubed minus 12x squared. Now we want to solve that equal to 0. That's the condition for a stationary point. So we've got 4x cubed minus 12x squared is equal to 0. How do we how do we solve that? It's best to factorize anything. Get it as a product equal to 0, because then you know you can take each part of your product and say that must be 0. So taking out the highest common factor would be our 4x squared, and that will leave us with an x minus a 3. Then we know that if this product is equal to 0, then either this must be 0, and if 4x squared is equal to 0, then x must be 0, or this bracket might be equal to 0, and that would mean x must be 3. So we've established there are 2 stationary points, one at x is 0 and one at x is 3. So stationary points occur at x is 0 and x is 3. To determine their nature, we need to test what's going on either side. So we set up our little tables with our 0 and our 3 as our central x value. A little bit to the left is a -1, a little bit to the right is +1. Check what the gradient is doing at those 2 x values. So I sub -1 into f dash x, and you can see I've done that here. 4 times, because my f dash x is this, 4 times -1 cubed minus 12 times -1 squared, we end up with a negative. So the gradient to the left of 0 is a negative, it's coming down. At x is 0, the gradient is 0, we know that. But when I sub in x as 1, then I also get a negative gradient. Negative gradient, 0 gradient, negative gradient. I conclude that that is a point of inflection, and I've done that here. At x equals 0, there is a point of inflection. At this point, I haven't really shown that concavity changes, but you'll see that I do that in the next section. Over at x is equal to 3, what's going on? Well, if we know that when x is 1, we get a negative gradient. We don't need to redo that one. X is 3, we've got a 0. And at x is equal to 4, I didn't actually show the working for that, but you do get a positive. So we've now got, at x is equal to 3, a minimum occurs. So we've got a point of inflection and a minimum so far. Part 2 asked us to identify points of inflection, and to do that you must solve the second derivative equal to 0 and show that concavity changes. So second derivative is 12x squared minus 24x. Solving it equal to 0, we get this x equals 0, which we were expecting, because back here we established at x equals 0, not only is it stationary, but it's a point of inflection. So we're getting that, we expected that. The unexpected, the one we didn't pick up previously, is that there is a point of inflection at x is equal to 2. Now, we need to establish that these really are points of inflection, and the way that you do it is to show that concavity changes. At x is equal to 0, we're now subbing into the second derivative, either side of 0. And to the left, when we sub into this expression, you get a positive. What does that tell me? It tells me at x is -1, the graph will be concave up. Now this is important because the third step of this, or the third part to this question, was to sketch the graph. So I've got concave up, and at x is 1, I've got concave down. And over at x is equal to 2, which we hadn't previously identified as a point of significance, we've got, well, at 1, we know that the second derivative was a negative, just carry that on. So it'll be still concave down until we get to 2, where something is happening. And I didn't go to 3 because at 3 there was a point of inflection, a stationary point. So I checked at 2.5 and I found that it was concave up. I would try to always avoid, when testing concavity, I'd try to avoid the stationary point. You don't have to, but I just suggest you do. So what do we know now? This was not something that we'd previously established, but it would be something that you would do when you're asked to sketch. Now moving on to the sketch. I suppose we should have concluded back here that at x is equal to 0 and as x is equal to 2 are points of inflection. At x is equal to 0, it's a horizontal point of inflection, and at x is equal to 2, it's just a straight point of inflection. So when we come to sketching, I always want to know when x is 0, what's going on, and when x is 0, y will be 0. We're back to the original function, which was x to the 4th minus 4x cubed. So we know that there's a turning point here. No, we know there's a point of inflection here, and we know that this is where it cuts the x-axis and the y-axis. To find where it cuts the x-axis, or if it cuts it any more, then let's solve our original function equal to 0. Y is 0 all along the x-axis. Factorising again, and you get again 0 and 4. So we had the 0, but now the point we didn't have, which is that on the graph cuts back through the x-axis at x is 4. Now in drawing the, sketching the graph, we had, remember, that at x is equal to 0, we've got a point of inflection. Before it, it was concave up, and after it, it is concave down. We're going concave down. We're going concave down until we get to 2. So we're going concave down all the way to 2, and at 2, we've got another point of inflection, and even at 2.5, we've got to be concave up. And we know that down at 3, we've got a point of inflection. So I haven't really drawn that very well. Hang on. Our critical points are here at 2, where I flip from concave down to concave up, and at 3, I've got a turning point. Remember that? A stationary point. So somehow I've got to go concave down, concave up, all the way over until x is 3, and then back through there. So I should be able to make that a bit more smooth. It's not a very pretty graph on my behalf, but you get the idea of what it should look like. So definite turning point there, and stationary point here. That stationary point ended up being a point of inflection. This stationary point was a minimum. This was also a point of inflection, and so was at x is equal to 2 a point of inflection. So that's how we use calculus to help us to sketch. You can see I've never drawn up a table of values to sketch this graph. I've just used my calculus. And let me stop the video.